This is section 9.1, part A, significance test, the basics. A significance test is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion P or the population mean mu. We express the results of a significance test in terms of a probability that measures how well the data in the claim agree. So statistical tests deal with claims about a population. Tests ask if sample data give good evidence against a claim. A test might say, if we took many random samples and the claim were true, we would rarely get a result like this. To get a numerical measure of how strong the sample evidence is, replace the vague term rarely with a probability. Here's an example of this reasoning at work. A virtual basketball player claims to be an 80% free throw shooter. Suppose that he shoots 50 free throws and makes 32 of them. His sample proportion of made shots is P hat is equal to 32 out of 50 or 64%. What can we conclude about the player's claim based on the sample data? Let's perform a simulation to find out. Our reasoning is based on asking what would happen if the player's claim that they are an 80% free throw shooter were true and we observe many samples of 50 free throws. So we used a Fathom software to simulate 400 sets of 50 shots, assuming the player is really an 80% free throw shooter. The below figure shows a dot plot of the results. Each dot on the graph represents the proportion of made shots in one set of 50 attempts. The proportion of made shots in one set of 50, for example, could be 43 out of 50, which would be at the far right of our proportion, or it would be at 0.86. So if we look at all 400 sets of these 50 shots, the ones that are circled on the left, there are only 3 times out of all 400 where a shooter made as few as 64% of the shots. So 3 out of 400 is not very likely. You can see how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he were actually an 80% free throw shooter in the long run. Based on our simulation, there was only 3 times out of the 400 we made 64% or less, which is 0.0075. The observed statistic of p hat of 0.64 is so unlikely if the actual parameter value is 80% that it gives convincing evidence that the player's claim is not true. Be sure to understand why this evidence is convincing. There are 2 possible explanations of the fact that our virtual player made only 64% of his free throws. First, the player's claim is correct, but he had bad luck. But this is a very unlikely outcome because we said it's a less than 1% chance that would happen based on our sample of 400. Or the population proportion is actually less than the 80%, so the sample result is not an unlikely outcome. Explanation 1 might be correct. The result of the random sample of 50 shots could be due to chance alone. But the probability that such a result would occur by chance is so small, again, it's less than 1%, that we are quite confident that it's actually explanation 2 and that he's not actually an 80% free throw shooter. Statistical tests use an elaborate vocabulary, but the basic idea is simple. An outcome that would rarely happen if a claim were true is good evidence that the claim is not true. A significance test starts with a careful statement of the claims we want to compare. If our free throw shooter example, the virtual player claims that his long-run proportion of made free throws is 80%. This is the claim that we seek evidence against, and we call this our null hypothesis. And we write our null hypothesis, it's going to be H sub 0, because null is the same thing as none. Usually, the null hypothesis is a statement of no difference. So you want to say your null hypothesis is always something equals something. You don't want to say less than, greater than, not equal to. Your null hypothesis is always going to be the one that equals something. It's not different. From the free throw shooter, no difference from what he claims would give us a null hypothesis of h sub 0 of p equals 0.80 or 80%. The claim we hope or suspect to be true instead of the null hypothesis is called the alternative hypothesis. We abbreviate the alternative hypothesis as h sub a because it's the alternative. In this case, we believe the player might be exaggerating, so our alternative hypothesis is going to be h sub a is p is less than 80%. The claim tested by a statistical test is called the null hypothesis. This is the one you're testing against. The test is designed to assess the strength of the evidence against the null hypothesis. Often, the null hypothesis is a statement of no difference. The claim about the population that we are trying to find evidence for is your alternative hypothesis, or your h sub a. In our free throw shooter example, our two hypotheses, our null hypothesis is that p equals 0.8. Our alternative hypothesis is p is less than 0.8, where p is the long-run proportion of made free throws. The alternative hypothesis is a one-sided hypothesis because we are interested in only whether the player is overestimating his free throw shooting ability. Because h sub a expresses the effects that we hope to find evidence for, it is sometimes easier to begin by stating your h sub a and then setting up your null hypothesis as a statement that we hope for effect is not present. Here is an example of an alternative hypothesis that is two-sided. So does job satisfaction of assembly line workers differ when their work is machine-based rather than self-paced? One study chose 18 subjects at random from a company with over 200 workers who assembled electronic devices. Half the workers were assigned at random to each of two groups. Both groups did similar assembly work, but one group was allowed to pace themselves, while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups and took the test again after 2 more weeks. This experiment is an example of a matched pair design, which we talked about in Chapter 4. So we're going to compare just one worker's test results after having a fixed pace and compare that result with just their test from the self-paced, and we'll do that for each individual worker. This is why it's a matched pair design. The response variable is the difference in satisfaction scores of self-paced minus machine-paced. Describe the parameter of interest in this setting. So the parameter of interest is the mean of the differences of self-paced minus machine-paced in job satisfaction scores and the population of all assembly line workers at this company. State appropriate hypotheses for performing a significance test. So your null hypothesis is always going to be either p equals something or mu equals something. In this case, we're going to assume that there's actually no difference between the two ways that they could be paced. So we're going to let our null hypothesis be that mu equals 0. And then we don't know if it's going to be better or worse. So we're going to let our alternative hypothesis be that mu does not equal 0. We don't know which one's going to be better, so we're better off to just say, I don't think it's going to be 0, but it could be better or it could be worse, so it's just not equal to 0. Now you do need to be cautious. The hypothesis should express the hopes or suspicions we have before we see the data. It is cheating to look at the data first and then frame your hypotheses to fit the data. So we didn't want to look at what the actual assembly line workers had and then say, well, we think mu is greater than 0. We want to set our hypothesis before we see any data so that we're not swayed by what the actual data already says. So the alternative hypothesis is one-sided if we say that it is larger than or smaller than the null value. It's two-sided if we just say that it's different, so it's not equal to. So if you have P or mu, whichever variable you're looking at, is greater than whatever your H sub 0 is, or P is less than, then this is one-sided. But if it's P does not equal to whatever your null hypothesis is, then that would be a two-sided hypothesis. In any significance test, the null hypothesis has the form H sub 0 of parameter equals whatever your value is. The alternative hypothesis has one of the following forms. So it can be our parameter is less than the value, our parameter is greater than the value, or the parameter does not equal the value. To determine the correct form of the null hypothesis, read the problem very carefully. So another caution, hypotheses always refer to a population, not a sample. Be sure to state the null hypothesis and alternative hypothesis in terms of the population parameters. It is never correct to rate a hypothesis based on sample statistics. So you should never say p hat equals 0.64 or x bar is greater than 85. It should always be in terms of p and mu, and you should never use the values you have from your sample. You should only use stuff you have from the entire population. So let's check our understanding. For each of the following settings, describe the parameter of interest and state appropriate hypotheses for the significance test. So according to the website sleepdeprivation.com, 85% of teens are getting less than 8 hours of sleep at night. Janie wonders whether this result holds in her large high school. She asks a simple random sample of 100 students at the school how much sleep they get on a typical night. In all, 75 of the respondents say that they got less than 8 hours. So we need to determine what we're actually looking for. What's our value that we care about? So in this case, we're looking for a proportion. P equals the proportion of students at Janie's high school who get less than 8 hours of sleep. So again, your P value is talking about the entire population. In this case, the population is her high school. So our alternative hypothesis, or our null hypothesis first, is always going to be P equals, we're talking about a proportion, whatever it says about the entire population, which is 85%. So our null hypothesis is P is equal to 0.85. Our alternative hypothesis, we don't know if they're going to have more sleep or less sleep than this. So, or we're going to have a higher percentage of students get less than 8 hours sleep or less than 85%. So we're just going to let our alternative hypothesis be that P does not equal 85%. We're assuming in her high school that there is not 85% of their students that get less than 8 hours of sleep a night. We don't know if it'll be less or more than 85%. We're just assuming it's not going to be exactly 85%. As part of its 2010 census marketing campaign, the U.S. Census Bureau advertised 10 questions, 10 minutes. That's all it takes. On the census form itself, we read, the U.S. Census Bureau estimates for the average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect that the actual time it takes to complete this form may be longer than advertised. So we're going to describe our parameter of interest. Right now we're talking about the average amount of time. So this would be a mean problem. So our mu, or our parameter of interest, is the mean amount of time that it takes to complete the census form. Now our hypotheses are the null hypothesis is always that it equals whatever they say it's going to equal. So the null hypothesis is that it actually is going to equal exactly 10 minutes. And it tells you in the problem that we think it's going to take longer than that. So our alternative hypothesis is that mu is going to be greater than 10.